Okay, this is the 8th video in chapter 10. This is kind of part 2 of the VSEPR theory. And I'm going to do it kind of by way of example. I know a couple in that previous video, it may have been hard to follow some of the concepts I was talking about when I was talking about number of electron groups attached to the central atom. So let me kind of do this by way of example. One of the things I mentioned is that when it comes to molecular shapes and this model, this VSEPR model, the number of electron groups that can be involved in determining the molecular shape attached to a central atom can either be 2, 3, 4, 5, or 6. By the way, in theory, it can actually go higher, but the book kind of stops at 6, and anything higher than 6 is a little obscure anyway. So I'm going to kind of show some examples of real molecules, of Lewis structure depictions of molecules for each of these types, and kind of talk a little bit about the shape, and kind of look at the electron pairs that involved in each case. One thing I should also mention is that one of the common themes that comes up in this chapter when it talks about shape, it also talks about bond angles. In addition to the shape, truly the angles of involved in these shapes becomes important, and this becomes important in it's important in biosystems, and it's also important in analyzing reactions, and it'll become more important when we study organic chemistry next time. Okay, I'm going to start with this. So I'm going to start with again, we're going to go 2, 3, 4, 5, and 6. So let me start with the 2. So the common example of a central atom with 2 electron groups, the really basic one that we always think about is carbon dioxide. And again, there is not a when looking just at the carbon atom, there's only 2 groups of electrons bonded to carbon. It's this double bond on the right and the double bond on the left. This results in a linear shape for the molecule because both of these electron groups want to be as far away from each other as possible. So it creates a bond angle of 180 degrees when looking at this molecule, this shape. There are other examples, and I'll mention. I'll draw one. Beryllium dichloride is also shaped this way. And again, if you look at this, remember beryllium was one of those exceptions to the octet rule because it's electron starved. So in looking at the central atom, beryllium, there's only 4 electrons around that atom, but that's okay. That's one of these exceptions to the octet rule. So beryllium dichloride has the same sort of linear shape. Now, I'm going to quickly show an example of something that is not a linear shape because it's not really 2, even though you might think it's this way. But if you look at water, your first reaction might be, oh yeah, water's going to be linear also. But don't forget, water has these 2 extra electron pairs. So when looking at the central atom, oxygen, it is not surrounded by 2 electron groups. It's actually surrounded by 4. 1, 2, 3, 4. Okay, so water is not an example of the case of 2 electron groups. Okay, so and again, the molecular shape when you have 2 electron groups around the central atom is linear, and there's no deviations to that. The angles are always 180 no matter what. All right, let's go on to 3. So a bonding group of 3 forms a shape of an overall shape of trigonal planar, essentially a triangle, a planar triangle. And we've actually encountered a couple of examples already. I drew the carbonate anion before. Right? And here's an example of the central carbon atom surrounded by 3 electron groups. 1, 2, 3. If you remember, there were multiple resonance forms of this as well, but there's 3 groups here. Now, the angle between each of these bonds is 120 degrees, as you'd expect in an equilateral triangle. Now, you'd be tempted to say, well, hang on, isn't there some effect of the fact that one of these is a double bond and the others are single bonds? And that would be a nice thought, except for, remember, there was a resonance situation here where no single oxygen really has a double bond. They all kind of have 1 1/3 bonds. So in fact, when you look at the bond angles in carbonate, they all are exactly the same. They're all 120 degrees. Okay, that's different though from another example that I'm going to throw up here, which is formaldehyde. Now, this is a molecule that we haven't done the full Lewis structure on, but it's a real simple organic molecule. And I'm just going to skip ahead and show you that when you do the full Lewis structure analysis, it would end up in a situation like this. Okay, a central carbon surrounded by a hydrogen, another hydrogen, and a double bond to an oxygen. Okay, this also has the trigonal planar form because, again, the central atom has three electron groups surrounding it. However, the angles here are not all 120 degrees because, unlike carbonate, which essentially has one form, there are three resonance forms, but they all get kind of superimposed into one thing such that all the angles are the same. In this case, that's not the case. We have different atoms involved here. And what you'll see is that this double bond to the oxygen actually has it's almost like a bigger cloud. And so it pushes this angle, I'm going to exaggerate it, it pushes this angle so that the angle between the carbon and the hydrogen is actually less than 120 degrees. Okay, and you'll see this, that essentially double bonds will do this, but also even lone pairs, the unbonded lone pairs, also have the same effect, is that they end up repelling more, repelling the other pairs more so, which tends to compress these angles. And you'll see other examples of this as we go. Okay, I think that's all I want to talk about with trigonal planar. Is there another example I wanted to show? No, it's formaldehyde carbonate. SO2 is another one. I'll draw the SO2 just for fun. This is acid rain, the nasty sulfur gas. SO2 is a sulfur with a lone pair. Well, sorry, we're not drawing them that way. SO2 has a lone pair and a double bond to two oxygens. Okay, and this is, again, looking at the sulfur as the central atom. It's surrounded by three electron groups, one to each oxygen and an unbonded lone pair. Okay. By the way, this is your first glimpse at a Lewis structure depiction of a central atom that has more than an octet. Sulfur, in this case, you can see the way I've drawn SO2 has 10 electrons around it. And we'll spend quite a bit of time talking about this as we go. I hope it's 10, maybe it's 12, but we'll get into this more later. All right, that's it for trigonal planar, which is the shape when a central atom has three electron groups around it. Okay. All right, now let's move on to 4. 4 is definitely the most common. Most common. Yeah, I guess it is. It's certainly the most common in organic chemicals, and that's an important group of chemicals, obviously. So in 4, again, the standard case that we drew, I've drawn several times. One is, of course, good old methane, and methane, we've got central carbon surrounded by 4 hydrogens, and they're all as far away as possible in a three-dimensional space, which is forming this shape, which is called a tetrahedral. And the bond angle, each of the bond angles is 109.5 degrees. That's a bit hard to kind of wrap your head around because it's in 3 dimensions, but I think if you look at the book or you look at other three-dimensional depictions of a tetrahedral, you can convince yourself that, yeah, that makes total sense. Okay. And carbon tetrachloride was another one of these chemicals that I originally depicted when we did the Lewis structure. And so they all form perfect tetrahedrals. Okay. Now, there's another important group of 4 is ammonia. And I depicted this once already. Ammonia has an unpaired with 3 H's. And so from an electron pair standpoint, they form basically a tetrahedral as well. However, it's not actually, the bond angle, unlike methane and carbon tetrachloride, the bond angle between the hydrogens is less than 109.5 degrees. And that is because the lone pair of electrons on the nitrogen atom actually repel more, a little bit more than let's say, another hydrogen would, right? Another hydrogen, this would be ammonium. We've seen this before. And ammonium forms a perfect tetrahedral shape because each of the electron clouds involved are the same. They're all symmetric amongst each other. However, in ammonia, that's not the case, and the lone pair actually repels a bit more. So here in this case, the angle between the nitrogen and the hydrogens is less than 109.5. I think it's 108 or something like that. It's in the book. Now, the shape of this molecule is not tetrahedral, and again, this is actually where it's a bit confusing. But they talk about electron configuration shapes, and that's what I'm doing here with the 2, 3, 4, 5, 6. But then they also talk molecular shape, and the molecular shape here is just focusing on the atoms. This has a different shape, and it's called trigonal pyramidal. Okay, and it's kind of shaped like a pyramid. Another one along the same when we're talking about 4 is water, and I mentioned this briefly too. I think again, water has 4 electron groups around the oxygen. 2 of them are bonds to hydrogen, but the other 2 are these electron pair groups. And so the shape, even though the electron configuration has a dimension of 4, the shape of this molecule is called bent. And again, the angle is bent here because the electron pairs repel down and make this bent shape. Okay. All right. Then we got 5 and 6, and I'm going to do these really. Well, maybe I shouldn't. I'm going to end this one, and I'll do 5 and 6 next, and then start talking about some problems.